Hi, my name is Nurul Natasha binti Abdurrahman and I will talk about the first question, that is when an electrical signal is converted to sound by a speaker. The loudness of the sound depends on the amplitude of the signal applied to the speaker. Based on this, explain how the volume control potentiometer is used to adjust the loudness of the sound. A potentiometer measures an unknown voltage by comparing it to the known voltage. A volume control potentiometer adjusts the volume in audio device like speaker, amplifier, and mixer by regulating the electrical signal sent to the load. Next, about the terminal, there are three terminals. First is an input for the audio signal, second is a ground for system reference, and the last is output connected to a movement wiper that adjusts the signal strength. After that, about the operation, by turning the knob, the wiper moves along a resistance strip, changing the resistance and adjusting the volume. Low resistance allows more signal to pass, making the sound louder. Meanwhile, the high resistance reduces the signal, making the sound softer. Then, the wiper position controls the signal. Closer to the input means higher amplitude and louder sound, but closer to the ground lower the amplitude and making the sound softer. Lastly, about the advantage, potentiometer offers smooth, precise volume control without sudden changes. Logarithmic type are used because human hearing naturally perceives sound on the logarithmic scale, making adjustment feel natural and intuitive. That's all from me, and I will pass to the next presenter of question 2.
Thank you, Nurul Natasha. My name is Alicia Ong Ishan. So now I'm going to present about question 2, which is explain with suitable diagram why RMS voltage is not same as peak voltage. So first, peak voltage represents the maximum voltage in a waveform, which is measured from the zero reference point to the highest crest. This value is crucial because it shows the amplitude of the waveform, which helping in ensuring that the electrical components can safely handle the highest voltage they might encounter. So as we can see in the sine wave diagram on our slide, we can see that the peak voltage at the highest point of the wave. To calculate the peak voltage, we can use these three formulas, which is first, from peak to peak voltage, divide by 2. Second, is from RMS voltage multiplied by square root 2, plus from average voltage multiplied by pi per 2. Next, RMS voltage measures the effective voltage of an AC waveform. It is equivalent to the DC voltage that would deliver the same power to a resistive load. Unlike peak voltage, RMS voltage reflects the actual energy delivered over time and is a critical parameter for power calculations. It considers the voltage variation throughout the waveform. In sinusoidal waveforms, RMS voltage can be calculated as RMS voltage equal to peak voltage divided square root 2, which approximately 0.7071 times peak voltage. Now, let's look at the key difference between RMS voltage and peak voltage. First, RMS voltage represents the effective voltage over time, which is equivalent to the power of DC voltage, while peak voltage refers to the maximum voltage that the waveform reaches at any given moment. Second, the purpose of RMS voltage is to calculate power since it reflects the energy delivered over a period, while peak voltage is useful for understanding the highest voltage a component might experience. Third, when it comes to a waveform behavior, RMS voltage takes into account the entire voltage cycle by averaging the squared values, while peak voltage only focuses on the highest point in the waveform. For in practical terms, RMS voltage is more significant as it determines the heating effect in resisting loads, such as light bulbs, and reflects real power transfer, while peak voltage does not provide information about the power delivering capacity of the waveform. Lastly, in sinusoidal waveforms, RMS voltage is always smaller than peak voltage, with a relationship of approximately 0.7071 times peak voltage. These differences highlight the importance of understanding both values for designing and analyzing electrical circuit effectively. That's all from me. So now I will pass it to the presenter of question 3.
Hello, my name is Muhammad Ishraf bin Karim Samsudin and I want to explain about the third question, that is the controversial issue of Bakundam in Sarawak. Before that, I want to talk about the history of Bakundam construction in Sarawak. Bakundam is located at the Bala River in Sarawak, Malaysia. The construction began in 1996. The dam opened in July 2014 after being completed in 2010. The maximum amount of power that may be generated by this Bakundam is 2,400 megawatt. Bakundam was built to meet growing demand for electricity in that area. Next, I will talk about the controversial issue of Bakundam in Sarawak. The first controversial issue of Bakundam is environmental impact. This had happened due to the submergible area of rainforest. The habitat for the animal and plant has been affected due to the massive deforestation. Not only that, the deforestation also released stored carbon into the atmosphere, thus contributing to climate change. This finally will affect local people who are dependent on forest resources such as food, medicine, and others more. After that, another controversial issue is the displacement of indigenous communities. Many indigenous communities were relocated to regions with limited resources and infrastructure. This has caused them to be unable to take part in the cultural and economic activities that they would normally do. Furthermore, the process of resettlement has been criticized for its weak planning and implementation. This has caused many indigenous people have faced the problems in adapting to their new environments. Last but not least, third controversial issue that has arisen is the disruption of aquatic ecosystem. This has happened because the construction of the Bakundam has disrupted the normal flow of the river. This caused fish species that migrate upstream to be trapped in a large reservoir. This finally will impact the survival and reproduction of aquatic organisms, thus leading to declined biodiversity and the degradation of water quality. That's all from me. Next, I will pass to the presenter of the question 4.
Thank you to Muhammad Ishraf. My name is Muhammad Fahmi Aiman bin Shuim. So now I would like to continue with the question 4, which are the analysis of half cycle average voltage in a simple resistive circuit. The concept of half cycle average is crucial in understanding the behavior of AC waveform, especially in power electronic and signal processing application. By focusing on half cycle, it will provide insight into signal characteristic while reducing computationally complexity. This method is particularly valuable for evaluating asymmetric waveform or understanding the behavior of a system over a limited period of time. This slide presents the circuit diagram under consideration. We have a simple resistive circuit with resistor R1, R2, and R3 connected in a series. The circuit is driven by an AC voltage source. Here we calculate the half cycle average voltage across each resistor. The formula for half cycle average voltage is provided. We utilize the RMS voltage value and resistance to determine the average voltage across each resistor. The result of the calculation show that the half cycle average voltage across R1 is 49.517 volt and across R2 is 31.511 volt. This result can be verified using simulation software like Multisim, which allow for a more accurate representation of the circuit behavior. In summary, we have successfully determined the half cycle average voltage across resistance R1 and R2 in the given circuit. This analysis provides valuable insight into the behavior of the circuit under AC excitation. Half-cycle average values are essential for various engineering applications, including power electronics, signal processing, and control systems.
Thank you to Fahmi Aiman. My name is Nur Christina Natasha. Now I would like to continue with question 5, which are maximum and minimum values of the resulting waveform that have a sine wave with an RMS value of 10.6 voltage is riding on DC level or 24 volt. So sine waveform is the most well-known and frequently utilized predict wave of electrical and electronic engineering that can apply in signal modulation, power electronics, and communication system. So this waveform combines the AC, alternating current, and DC, direct current. So to get the maximum and minimum value of the waveform, we calculate using theoretical calculation, which is using the formula of VRMS equal to V peak divided by square root 2, because the RMS value of 10.6 volt is a measure of the effective voltage of the sine wave. So the peak voltage, which is V peak of the sine wave, is related to the RMS value by calculating it with V peak equal to VRMS times square root 2, where 10.6 voltage times square root 2, and we got the value of V peak is 14.99 volts. After that, the DC voltage shifts the entire sine wave vertically by 24 volt, and therefore, when the sine wave is at its peak, which is 14.99 volt, the total voltage is Vmax equal to VDC plus V peak, where 24 plus 14.99, and we get the maximum value is 38.99 volt. And when the sine wave is at its trough, which is negative 14.99, the total voltage at Vmin equal to VDC minus V peak, where 24 minus 14.99, and we get the minimum value is 9.01 volt. Okay, to prove this, we utilize the multisim software to get the simulation of each circuit and the sine waveform. First, we look at the simulation of the circuit. In this circuit, we have 4 components, which is the first one is V1. This voltage source is a DC that provide a value of 24 volt. The entire AC waveform from V2 is shifted upward by 24 volt. As a result, it producing a DC offset. Second, V2 is an AC voltage with root mean square RMS value of 10.6 volt at a frequency of 16 Hz. Third, we have resistor, which is R1, where a 1 kilo ohm resistor limits the current flow through the circuit. And the fourth one is we have the SC1, where it used to present the waveform that is produced when the DC voltage from V1 and the AC voltage from V2 are superimposed. Now we look at the simulation of graph for maximum and minimum value in the sine waveform. The waveform that results from adding a 24 volt DC and an AC sine voltage with an RMS of 10.6 volt is shown in the graph. The waveform moves between the maximum peak and the minimum peak on the graph, with the maximum voltage at 38.66 volt and the minimum at 9.357 volt. After that, the graph shows a waveform with a sine wave oscillating around a 24 volt DC offset. The DC voltage then causes the sum of the wave to be shifted higher as well, making the minimum value above 0 volt. As a result, both values show results that are close to the theoretical calculation, where the maximum value is 39 volt and the minimum value is 9.01. As a result, it can be concluded that the multisim simulation successfully validated the theoretical calculation, where it demonstrated the most valuable accuracy. Therefore, this study indicates that a sine wave with an RMS of 10.6 volt riding on a 24 volt DC level produce a waveform with a maximum of approximately 39 volt and a minimum of approximately 9 volt. So, I think that's all from our group. Thank you.